Okay, today we start talking about the LP spaces. We first introduced several important inequalities that are used almost everywhere in the study of LP spaces. First, we'll give the definition of the LP space. So suppose we have a measurable set, which is E, and then let's say P is a number, positive number, that could be infinity. Then the LP norm of the function f on E is given by the follows. We use the notation f p to denote this norm, and it's defined as the integral of the function f with power p as integrand, and then after we take the integral, we take the pth root. Okay, so this is for any p greater than 0, less than infinity, and the p is, if p is infinity, this is just the essential supremum of the function f, which is defined as the real number m, such that f is bounded by this m almost everywhere on E. Okay, so let's first look at this one. So it's whatever the function is, you take the p's power, and then you take the integral. So this is a non-negative value, and then you take the pth root. Right, so that's for the p finite value p. And if p is infinity, then this essentially here, so here means that the function f is uniformly bounded by m, or it means that except for a measure zero set, the value of f is bounded by m. And the smallest possible, or the infimum of those m, is called the infinity norm of f. This is also called the essential supremum. Supremum of the function f. Okay, and also if p is between 0 and infinity, then the LP of E is just the set of functions whose LP norm is finite. And similarly, if p is equal to infinity, the L infinity norm V is just the set of functions similar to above. It's just that the infinity norm is finite. So in this case, this just means that there exists some m such that the f is bounded by that m almost everywhere. Okay. So now let's take a look at the relation between LP and L infinity. Actually, you can treat the L infinity norm as a limit of the LP norm as p goes to infinity, in some sense. Okay, and in what sense? If the set E has a finite measure, then we can show that the limit of the LP norm as p goes to infinity is equal to the F infinity norm. Oh, by the way, so sometimes the people write this as the p norm or infinity norm. Sometimes they write this as, if they want to specify where the domain is, you usually use the LPE, okay, to denote it. But in this course, let's say we fix the set E, then we only talk about the integration over this measurable set E, then we can just simply write it as that. Okay. All right, so let's show this limit. Okay, so first of all, since this function f is this set E is given that has a finite measure, and the function f is given, so we set m to be the infinity norm of f, and then we can see that the infinity norm of p of f, sorry, the p norm of f as definition is equal to, let me just write things in shortcut, it will be this. And now that the p is positive, so I know that this since we have this positive power here, so when we increase this, the value of the whole thing will increase as well. This is the negative value. So we know that inside this is less than or equal to the integral of m to the power p. The reason is that f is bounded by m almost everywhere, and the p is positive. I do have this. So that's why we can just show that this is less than or equal to e mp power p. And then we can see that this m to the power p is a constant, so it can be pulled out. So it's just equal to mp, the integral of 1 for the set E to the p's power. And then this is equal to m, and the p and the 1 over p canceled. And we have this part is just a measure of E. So it's the measure of E to the power 1 over p. And since this measure is finite, I know this value is a finite number. So as p goes to infinity, this thing goes to 1. Right? So this goes to m as p goes to positive infinity. Okay, and this shows that the upper limit of fp is bounded by m. Okay, now we only need to show that the lower limit is greater than or equal to m. Okay, to show that, we can show that for any epsilon, there we let the set A to be the set of points where the function f is bigger than m minus epsilon. Okay, and we can see that this A has a positive measure. Okay, this A has a positive measure. The reason is if the measure of A is equal to 0, then that means the f is bounded by m minus epsilon almost everywhere, right? So see that this must be greater than 0, because if not, then the mu of A is equal to 0, which means the f is bounded by m minus epsilon almost everywhere. And in this case, m minus epsilon will be the L infinity norm of f, which is contrary to, or which is contradiction to that. Okay, we found an even smaller value to be the L infinity norm of f. So that's a contradiction. So then that means that the measure of A must be greater than 0. Okay, and because of this, we can show that the p norm of f, or the LP norm of f, is equal to the integral of f p over p, and apparently it is bigger than, again, inside the p's root, we know that the integral is bigger than or equal to that, because we're taking the integral over a smaller set A. Okay, and we know that over this set A, this is the f is bigger than m minus epsilon, so that's why it is bigger than or equal to the integral A m minus epsilon p, and then 1 over p. And again, this we can pull out the constant, and then it's just become the m minus epsilon times the mu of a to the power 1 over p. And since this is a positive number, so as p goes to infinity, this whole thing just goes to 1. Just goes to 1. Okay, and then we have this goes to m minus epsilon. So that means the inf, or the lower limit of fp as p goes to infinity is bigger than or equal to m minus epsilon. Okay, and because epsilon is arbitrary, we know that the lower limit of this p norm of f is bigger than or equal to m. And combining with the fact here, we know that the limit, the upper limit is lower than or equal to m, is bigger than or equal to the lower limit of the norm, but it's also greater than or equal to m. So we know that the limit must exist, and it is equal to m. Okay, so that's okay. So this inequality is because the epsilon is chosen arbitrarily, so that's why this must be greater than or equal to m. On the other hand, we know that it must be smaller than or equal to the upper limit, but this is less than or equal to m. So we can see that this, since this is m, this is m, then everything in between must be equal. That's why the limit must be equal to m. So the limit exists, and this is equal to m. Okay, so next, let's show that for any LP space, for any p, the LP space is linear. Okay, so we just need to show that any linear combination of functions f, g in P, LP is still in LP. Okay, so let's again consider the case P is finite and infinite separately. Okay, so to prove this, the case for P, finite P, let's recall that, let me recall that the following inequality. So for any real numbers, non-negative real numbers, there is, okay, I'm going to take the P's power of u plus v. So P is positive and finite. Let's say P is finite and positive. And in this case, in the inside parentheses, this is less than or equal to 2 times the maximum value of u and v, right? Because that this is less than or equal to this. Okay, so I can take the P's power of that, and now we got 2 to the power p, and the maximum of u and v take the power p is, since the something to the power p is a increasing function, so it's just the maximum of u to the power p and v to the power p. And this here is less than or equal to the sum of these two, because both are non-negative, right? So that's it's less than equal to this, u to the power p plus v to the power p. Okay, so we can show that this is true for any non-negative values u and v. So in this case, we can see that if p is, so here is also p is actually between 0 and infinity, then we can see that the alpha f plus beta g to the power p, according to what we showed above, this is less than or equal to 2 to the power p times alpha f to the power p plus beta g to the power p. Okay, and this is equal to 2p alpha p times f p plus 2p beta p times gp. Okay, and then we can take the integral on both sides. You can see that this to the power p is less than or equal to 2p alpha to the p integral of f to the p plus 2p beta p integral of g to the p. Okay, and then we know that on the right hand side, this is finite because the f is in our p, so the p's root of this is finite. That just also means that this is finite. So actually, by the way, when we define that, we can not just define this to be less than and to be finite. We can just say that is finite, or just that this is finite. Okay, because it takes the p's root, it will be finite as well. Okay, so that's why this is finite, and because it's finite, we know that the alpha f plus beta g is in our p. Okay, so that's the case where the p is a finite. If p is infinite, then it will be even easier, because if this is the case, then we can see that the alpha f plus beta g is less than or equal to alpha f plus beta g. For every x, for every point x, we have this, but since this is bounded by that almost everywhere, so that means this is bounded by that, almost bounded by this thing almost everywhere for every. So because this is all x for all the physical s, so it's bounded by the right hand side, which is a finite number independent of x. So that's why this is bounded by a fixed number almost everywhere, and that implies that they are also in, this is also in L infinity. Okay, so that's true for almost everywhere. For less than this, almost everywhere. So that's why this is a in R infinity. Okay. Next, let's give a definition for conjugate numbers. We say that two numbers p and q that are both greater than 1. We actually can extend it to greater than or equal to 1. Let's just say this. Our conjugate if 1 over p plus 1 over q is equal to 1. Okay, so this is a beautiful relation between the two numbers. So for example, if p is equal to 2, then q is also equal to 2. Okay, so this is the most symmetrical case, but p could be some other number as well. But let's say restrict that p to be greater than 1. In this case, 1 over p will be less than 1, so that will give some space for 1 over q, and q will be also a number bigger than 1. Okay, it special case is what I said, is both equal to 2. But any other value will work. And actually, we can solve for given p, we can solve for q. That q is equal to p over p minus 1. we can show that. Okay, you can easily solve for Q and you get that. So when you see the Q to be equal to that, then you can immediately tell that P and Q are conjugate to each other. Okay, so this is the case where the P and Q are both greater than 1. But we can also consider extreme case where P is equal to 1. So if P is equal to 1, then according to this formula, you can see that the 1 over Q must be equal to 0. And in this case, Q is infinity. Okay, and or if P is infinity, then Q is equal to 1. Okay, and we do not consider the case where P is less than 1, because if P is greater than 0, less than 1, then this will be a number bigger than 1. And then in that case, Q must be negative. Then we're not interested in that case. Okay, now let's move on to the several inequalities that we need. The first one is called the Young's inequality. Okay, I have to say that these inequalities are extremely important. They are used not just in analysis, but in many related fields like partial differential equations, functional analysis. Okay, so it's called Young's inequality. Okay, so let P and Q be conjugate. Which means this, right? 1 over P plus 1 over Q is equal to 1. And for any UV greater than or equal to 0, there is U times V is less than or equal to U to the power P over P plus V to the power Q over Q. Okay, so a special case is when P and Q are both equal to 2. In that case, we just have U times V is less than U squared over 2 plus V squared over 2. And this one is you should be very familiar with this one. Right? UV less than or equal to half of U squared plus V squared. And this can be obtained easily in some inequality you know. But in general, as long as P and Q are conjugate to each other like that, then we have this inequality. So the Young's inequality is a generalization of that inequality we just wrote. Okay. The proof is this. If U equals to 0 or V equals to 0, then we know that the left-hand side must be 0. The right-hand side must be greater than or equal to 0, since we assume that this is greater than or equal to 0. So then the inequality must hold. So which is trivial. So we're only interested in the case that both are non-zero. Okay, suppose they are both non-zero. Then let's consider, let's look at this. This is 1 over P plus 1 over Q equals to 1. This is basically like this is like a lambda. This is like a 1 minus lambda, where lambda is between 0 and 1. Okay, so you know that this is pretty common from for convex functions. You have a convex function f. That means by definition of convexity, the f will be satisfy this, which is lambda x plus 1 minus lambda y is less than or equal to lambda times f of x plus 1 minus lambda times f of y. Meaning that if you take the convex combination of x and y first and take the applied f, will be less than or equal to you apply f to each of these 2 points separately, then take a combination of the values. So this is the definition for f being convex. So the f is convex if and only if for any lambda between 0 and 1, this is less than or equal to this. Okay, and when lambda equals to 0 or 1, you don't need to worry, because when lambda equals to 0, you can see here it's just a y. And on the right hand side, lambda equals 0, this is gone, and this is just f of y. So you must have identity, equality. But what actually takes the power is that when lambda is between 0 and 1, for any number lambda between 0 and 1, you still have this less than or equal to that. Okay, so this is the property for convex functions. And you know that to check the function is convex, you can either use the definition, or if the function f is differentiable, you can just check the second order derivative to see if it is greater than or equal to 0. If the second order derivative of f exists, then it's greater than or equal to 0 for all the x, then the f is convex. Okay, so it's equal to that if the f is in C2, for example. Okay, and now you can easily check that the many functions can be easily checked for convexity. For example, say ex. If fx equals to ex, then we know that the second order derivative, if you take a derivative twice, it's still ex. And that is greater than 0, and that means f is convex. Okay, and or if we check fx equals to, say, log of x, then we know that f prime of x is 1 over x, right? And the f negative log. So we'll take derivative once, we'll have negative 1 over x, and derivative twice, and we know this is just 1 over x squared, which is greater than 0. And that also means the function is convex. So for example, this one, for the first one, the ex is like that, right? And the second one, so this is for the ex. The second one is the negative log, which is this. So this is negative log of x, which is convex. Okay, and you can easily check this for many other functions. For example, if fx is e to the negative x, e to the negative x is this, which is also convex, because you take a derivative twice, you just have e to the negative x, which is still convex. Or you can check functions like x squared must be convex. Right? X to the power 4 would be convex, something like that. So it's just checking this, pretty easy. Okay, so now let's use that fact, especially use the fact that e to the power x is convex. Now the f is the e to the power x. Then we can see that the u times v, going back to this inequality, u times v can be written as e to the power logarithm. This log is the natural log u v, right? And then this is equal to the e to the power log u plus log v. All right, and then I can take the p's 1 over p times the log of u to the power p. Remember that u and v are positive, so I can put it in the log. And I put p's power on u, and this p's power can be moved out and cancel with the p outside, right? So this, I didn't really change anything. Also this, v to the power q. Okay, so now because the e to the x is convex, and we're taking, say, this as x, this as y, and this as lambda, this as 1 minus lambda. So I take the e to the power of that, must be less than or equal to, I take the e to each individual, to x and to y individually, and then take the combination. So it's less than or equal to 1 over p times e to the power log up, as I said, log of u to the p, this whole thing is like the x. Okay, so I'll have that plus 1 over q times e to the power log of v to the power q. And this is because that is looks like just y here. And now I can see that the e and the log will be cancelled, so we have just 1 over p, and u to the power p plus 1 over q times v to the power q, and that is the inequality we wanted. Okay, so that's how we show this inequality. Okay, it's pretty useful result that not just in analysis as well, but many related fields like partial differential equation in optimization. Okay, it's pretty common inequality. Next inequality is pretty famous. It's called the Holder's inequality. Okay, so what it says is that if p is 1 to infinity, the q is its conjugate. So we allow p to take a value 1. In that case, q will be infinity. If f is in our p, g is in our q, then we can show that this, let me write it in this way, the integral of f g, so you know the meaning of this, just fx times gx and take the integral. This is less than or equal to the 1 norm of fg, and this is less than or equal to the p norm of f times the q norm of g, where this p and q are conjugate, as we said. Okay. The first inequality is trivial. It's just because this is just equal to the integral of f times g, and we moved the absolute value to the integrand, so that's why we have the first inequality. So that's trivial. For the second inequality, this is what the Holder's inequality actually shows. We consider two cases when p is equal to 1. If p is equal to 1, then what we have is that we just need to show the second inequality, as we said. Then this is equal to the integral of that, right? But if p is equal to 1, then q is infinity, then the g has an infinity norm. That means the g is bounded by some m, capital M, so it's less than or equal to m, times the integral of f. And this one here is the infinity norm of g. And then this part is just the 1 normal of f, so it's just the f, 1 normal of f times the infinity norm of g. So that apparently is true for to show that when p is equal to 1, the q is to infinity. So now let's just show the case where p is greater than 1. Okay, so in this case, let's consider the integral of fg over the norm of fp, the g norm, q norm of g. Okay. By the way, the denominators will assume them to be non-zero, because if one of them is 0, if p norm is equal to 0, it doesn't matter what p is, positive, finite or infinite, we can see from here. That if the norm is equal to 0, then just means that this is 0 almost everywhere. Okay, or means this is 0 almost everywhere. And similarly, if this is 0, then that just means the function f is 0 almost everywhere. And in that case, the inequality must hold, because one of them is 0 almost everywhere. Then the left hand side is 0, and the right hand side is 0. So it's trivial. So we assume that neither of this is 0. They are both non-zero. Then in this case, we can divide put this on the denominator, and this is just a constant on the denominator, right? Two constants on the denominator, and then we take the integral, and then we know that this is just equal to fp. So here, to write it more specifically, this is actually fx over a constant, which is the p norm of f, times the gx we divided by the q norm of f. Take the integral, and we know that this, according to the Young's inequality, we can treat this as u, this as v, and in this case it will be less than or equal to the integral of the u to the power p divided by p. So it's this, and the p's power of f p, let me put the p outside, plus 1 over q, and the gx to the power q, again to the q outside. Okay, and it's a sum, so I can separate them, and this is just equal to 1 over p, and again this is constant that can be pulled out. Remember that I have a power p onto this, okay, and the inside is this, the power p dx e. So that's the first term. Second term similar, gq norm to the power q, and the f is gx to the power q dx. All right, so now realize that this is equal to the fp to the power p, right? Because the parenthesis itself is just to the power 1 over p is the LP norm of f, and then this is the parenthesis just equal to the q norm, q's power of the q norm, and then they cancel, right? Because this one is the same as this, so they will cancel, which is equal to 1, and this is equal to 1. So that's why we just have 1 over p plus 1 over q on the right hand side, but this is equal to 1 because the two are conjugate to each other. It's a beautiful result that we just end up with 1. And then now we show that this is less than or equal to 1. But this one is just a constant, so can pull it out, and I can even multiply it by on both sides. I will just get the integral of fg dx is just less than or equal to the fp norm times the p norm of f and the q norm of g. Okay? And that is the second inequality that we wanted to prove, which is called the Holder's inequality. Okay? So that's the Holder's inequality, also very, very famous. A special case of the Holder's inequality is called Schwarz inequality, which you probably have seen this many times. Schwarz inequality. And that is the case where we choose p and q equal to 2. Okay. Actually, this is just not. It's not only hold for functions f, g. If you have two vectors, say f and g are two n-dimensional vectors, then say if you have a vector x, let's see, vector u, so u is equal to the u1 up to un, then the p norm of u is defined as you take the sum of the p's powers of the components and take the p's root. And you basically can substitute all this f and g by these vectors u and v, which have the same dimension, and then we can also have the same inequalities, like the Holder's inequality and the Schwarz inequality. Okay? So they also hold for discrete functions. They're discrete vectors, not just functions. But in this course, we will consider the functions only. Okay? Discrete cases are pretty common in optimization. Okay, next theorem. Let's consider the case where if E is finite, then we actually have a embedding of the spaces. Say we have two numbers P1, P2. They could be less than 1. But the key is that the measure must be finite. The measure of the set E must be finite. Then we can show that the L2 space is embedded in the LP2 space is embedded in LP1 space. In which sense, it means that any function in here must be also in here. So this P2, remember that P2 is larger than P1. For example, P2 equals to 2, P1 equals to 1. Then L2 is embedded in L1. That means every L2, our function in L2 will be also in the space of L1. And that we must require this to be finite, right? Otherwise, it may not true. It may not be true. Okay. And more specifically, we actually have a relation between the norms of the two norms. So the P1 norm of F will be less than or equal to the measure of E to the power 1 over P1 plus 1 over P2. Remember, this is a positive power because P1 is less than P2. So 1 over P1 is bigger than 1 over P2. Also, is this. Okay, and this also explains why this is embedded in that, because if F is in this space, then that means this is finite. And since this is smaller than this right-hand side, and this is a finite number, and this is a finite number, so the right-hand side is also finite. So if F is in this space, then this is finite, and that also means this is finite, and that means F is also in this space. Okay, so let's see the proof. Okay, actually, see, this could be even infinity here, but if it's infinity, it will be trivial. If P2 is infinity, then apparently the P1 norm of F is just this. D, do not write D anymore. It's this to the power 1 over P1, and this must be less than or equal to the essential supremum of F, which is, let's call it M. So this will be less than or equal to M to the power P1 and integral over E of 1 times 2 to the power 1 over P1. And then apparently this is just equal to M times the measure of E to the power 1 over P1. Okay, and this right-hand side is nothing but the mu of E to the power 1 over P1 minus 1 over P2, but the P2 is infinity, so it's like just 1 over P1. And the M is the infinity norm. Okay, so we don't need to rewrite this, but this must be true since M equals to the infinity norm of F, and apparently this inequality holds. Okay, so it's easy. But if P2 is smaller than infinity, then we can do something similar. So this is the P1, right? And this is the integral of F to the power P1, 1 over P1. And this is equal to, we'll say that is equal to F to the power P1 times 1 to the power P1. And now let's treat this as the one norm of this times this. So this is like the F, this is like the G. And remember previously we showed the Holder's inequality showed that this inside is less than or equal to the P norm of F times the Q norm of G for conjugate the P and the Q. And now let's set the P to be the P1, P2 over P1, which is bigger than 1. And then the Q will be the conjugate of P, which is, as we said, is P over P minus 1. And then we can easily calculate this. Let me just actually write them down. So let's call that, let's set P to be P2 over P1, which is bigger than 1. The Q is a conjugate of P, then that will be P over P minus 1. That will be P2 over P1 over the P2 over P1 minus 1. You can easily show that it's just the P2, cancel out the denominators, will be just P2 times over P2 minus P1. Okay, and then we'll continue the derivation there. It will be less than or equal to the F P1. Let me write it in this way. It's the integral of E F of P1 times the P to the power 1 over P times the integral of 1 to the power Q to the power 1 over Q. And everything outside it will have 1 over P1. Okay, we just change the inside to this times this. So this is, as I said, it's like you treat this as your F, this as your G, and then there will be F to the power P, and then the P's root. And then here you have the 1 to the power Q and the Q's root. Okay? And then remember that P is equal to that, P2 over P1. So P1 times P will be P2. So this will be integral of F and then P2. And I have the P outside, and the P times P1. That's what I have outside. And the inside, another term I have here is a 1. It's mu E, which is the one here. And then I have a 1 over Q and then 1 over P, 1 over P1, so it's a 1 over Q P1. Okay, and now the first one is just equal to 1 over, just equal to the P2 norm of F, since this, when they multiply them together, is still just P2. So it's 1 over P2, and the inside is this, so it's just the P2 norm of F. And here, the Q is Q times P1. Q times P1 will be, here we write, over Q times P1. According to our Q above, it will be P2 over P2 minus P1 times P1. Okay, and this can be written as it's Q on the denominator, so it's that. So its Q is equal to P2 minus P1 times P1. So this is equal to P2 minus P1 over P2 P1, and that is equal to 1 over P1 minus 1 over P2. Okay, so that's why the second term is just mu E to the power 1 over P1 minus 1 over P2. Okay, that's exactly the inequality we had here. Okay, so you can see that it's pretty fun. It's just do some, just to make sure that you choose some power P and Q properly, and then apply the Hölder's inequality. You can usually get a very interesting result. All right, so that's the proof here. Okay, so now let's look at one more example. Again, it's to show some inequalities. So you have this function f that is in LR of E and also in LS of E. Okay, where 0 where r is less than s and p is in between. Okay, so here we don't require the e to have finite matter. It's different from the previous result, where if you want to have the embedding between the LP1 and LP2, you need to have this bounded domain, or the measure of the set must be bounded, it must be finite. Okay, here we don't require that, but let's see, we already know that f is in LR and in LS, so it's already in here. We want to show that it's also in here, in LP. Okay, to show that, let lambda to be between 0 and 1 such that the 1 over p is equal to 1 over r times lambda plus 1 minus lambda times over s. Okay, and you know this is true because if p is between r and s, then 1 over p is between 1 over r and 1 over s. So you know that we can find some convex combination of 1 over r and 1 over s to form this 1 over p. Okay, so this is how the lambda is. And we actually can compute what the lambda is if you like, but we don't really need that. You just need to know that lambda is such that this inequality holds. Then what we know is that the p norm of f is less than or equal to the r norm to the power lambda times the s norm to the power 1 minus lambda. Okay, we can show that. So basically we know that the squeeze is kind of squeezing this f such that the LP norm is also finite and it's bounded by the right side. Okay, so let's see a proof. One thing you can notice that if we multiply p on both sides, then we can show that the 1 is equal to, I have a lambda p on the numerator, but I put it on the denominator, plus 1 over the s over 1 minus lambda p. Okay, so we know that, right? Just multiply the p on both sides and flip all the numerator to the denominator. We have that. So we know that the r over lambda p and s over 1 minus lambda to p are conjugate. Right? We know that. Okay, so now we're going to apply the Holder's inequality. So consider the p's power of the p norm, and that's just simply the p's power of f, and take the integral. I don't specify the e, but it's just arbitrary e set e. It could be even have infinite measure. And then I'm going to split the p to two parts. Since I know lambda is a number between 0 and 1, so I can split that. I have to be lambda p and 1 minus lambda times p. Okay, so I have this. And now I can consider this as the f, this as the g. So I know that this is going to be less than or equal to, so let me write this, this is just less than or equal to f to the lambda p, and then I know that I'm going to have the r over lambda p as the, applied to the Holder's inequality with these two values, this value. So it's this norm of that times this norm of this term. So that's just 1 minus lambda p, the s over 1 minus lambda p. Okay, so let's see what this actually boils down to. The first term is just f lambda p, okay, and then it's times r over lambda p, and then it's lambda p over r. The second term is f with 1 minus lambda p times s over 1 minus lambda p to the power 1 minus lambda p divided by s. Okay, so start just separate them, and then you can see that the powers are cancelled. I have f to the power r, and then we'll have 1 over r, and then we have this whole thing times the power lambda p. Okay, and similar for the second term, this will be just the integral of f to the power s, then to the power 1 over s, then 1 minus lambda to the power p. Okay, so the left-hand side can, the right-hand side now can be written as the r norm of f to the power lambda p times the s norm of f times the power to the power 1 minus lambda times p. Now remember that both of the two sides, both sides have this p, so I can take the p's root. I will get the p norm of f will be less than or equal to the r norm to the power lambda, f's norm to the power 1 minus lambda, and that is the inequality we wanted. Will be the inequality we wanted. Okay. Now, let's move on to another example. Okay, say I have R, P, S again, as the order as before. F is in RP, and then for any t greater than 0, there exists, I want to show that there exists G and H such that F is equal to G plus H, and the R norm of G to the power R is less than or equal to T to the power R minus P times F P to the power P, and also the H norm, the S norm of H is less than or equal to T to the power S minus P times F P's P norm of F to the power P. Okay, so we call that, we just have again R and S, and the P is in between, and F is in our LP. See here, then we can show that for any t, there is two functions G and H, so that F can be decomposed into the sum, so that the one of them, the G has a R norm to the power R bounded by somehow the P norm of F with this term, additional term, and also the H has something similar. So we're going to show one of them, and the other one is just very similar. Okay, so we define G to be F times the characteristic function of F bigger than T. Okay, bigger than T. So it's just that if F is bigger than T, over the set F is bigger than T, G is equal to F, and otherwise G is equal to 0. Okay, so this is equal to F of X if the F of X is bigger than T, is equal to 0 if F of X is less than or equal to T. Okay, so now let's take a look at the G norm. So the R norm of G to the power R is just integral of G R, right? And this can be written as the G, I separate this to two parts. One is R minus P, the other part is P. Okay, they're all on E. And now that I know the G will be 0 when it's outside of this set. So actually, I can just rewrite this as just F bigger than T. And this is G, R minus P, G, P. And I know that over this set, the G is just equal to F. So I can actually replace this by F. since G is equal to F over this set. Sorry. Okay, and I know that F is greater than T, and this R minus P is negative. R minus P is negative. So I know this is a negative number, and the F is greater than T, so F, let me use absolute value instead. So it's absolute value of F, absolute value of F. Okay, absolute value of F is bigger than T. It's the same as the R minus P's power is less than T to the R minus P's power because this is negative. Okay, so I have this is less than or equal to the T R minus P, then this of the P norm, and apparently this is less than or equal to T R minus P, and you take the integral of this smaller set is smaller than taking the integral over the entire E, and that the right hand side become just FPP. Okay, that shows the first inequality. In the second inequality, and then once we choose the G like that, in this way, then we can just take H to be F minus G, and in that case, H will be just F times the characteristic function of this set less than or equal to T. Okay, and then we can show the inequality similar. Okay. Okay, let me show another example. They have the Fk, they are all in L2 over this interval. The Fk converts to 0 in measure. Fk has a true norm less than or equal to 1. And I want to show that the limit of this integral is equal to 0. Okay, so we see that Fk goes to 0 almost in measure, so we know that for any epsilon greater than 0, the set mu of Ek epsilon is going to 0 as k goes to infinity, right? Where this Ek epsilon is what we usually define. It's just a set of points where Fk is bigger than or equal to epsilon. All right, so now we can see that on the one hand, this Fk is greater than or equal to 0 because we're taking integral of non-negative value. And I separate this to two parts. One part is everything outside Ek epsilon. And the other part is just Ek epsilon, Fk. Okay, so I know that over this set, the F has a value less than or equal to epsilon, right? So this is less than or equal to epsilon times the mu of this set plus this second term is like the norm of this times the characteristic function of that, right? So we can use the Holder's inequality or Schwarz inequality. This is less than or equal to the 2 norm times the 2 norm of that, so just like this over 2. But this one here is just the mu of Ek epsilon, right? Because the integrand is equal to 1. So this is just taking the root of this measure. And we can see that as k goes to infinity, I know that this is less than or equal to 1. So this is less than epsilon plus the mu of Ek epsilon 1/2 times the 2 norm So this is less than or equal to 1, and this one here goes to 0 as k goes to 0. So that's why this goes to epsilon as k goes to infinity. And since epsilon is arbitrary, we know that the limit of this integral must go to 0, equal to 0. Okay, so I'm going to show the last result in this class. It's a very famous inequality called the Minkowski inequality. Okay, so suppose that p is between 1 and the positive infinity. Could take a value 1 and positive infinity. If f, g are in LP, then we can show that the p norm of f plus g is less than or equal to the p norm of f plus the p norm of g. Okay, so the significance of this result is that the LP space can have this p norm as a norm, as the actual norm, because we can easily show that the f of p is greater than or equal to 0, and is equal to 0 if and only if f is 0 almost everywhere. Right, that's the first one. Second one is that you multiply the f by any constant, say alpha times f p, it's just equal to the alpha times the p norm of f. And the third one is this triangle inequality given by this Minkowski inequality. Okay, so triangle inequality, and with the 3 here, we can show that this space of LP is a normal space, or the norm is given by this LP norm. Okay, so the proof: if p is equal to 1, then apparently this is just f plus g 1 norm, and that's just integral of f plus g. Right? That's just by triangle inequality is less than or equal to just this, and the right hand side is just f1 norm, 1 norm of f or g, and 1 norm of g, and apparently it holds. If p is infinity, then we know that this, or in other words, I should say, f of x plus g of x will be bounded by f infinity norm plus g infinity norm almost everywhere for x, and this implies that the infinity norm of f plus g is less than or equal to the infinity norm of f plus the infinity norm of g. Okay, that's also easy to show. And if p is between 0 and infinity, 1 and infinity, then let's consider the integral here. So this is the p's power of the p norm of f plus g, right? So we take the integral here, and I ignore set, but the set, because the set doesn't matter. It doesn't matter if it's finite. The matter is finite or not. Just any arbitrary set. We can show that this is equal to just split the power, because p is bigger than 1, so I can split to p minus 1 and p. And 1, right? And then this is less than or equal to same thing here, but I'm going to use the triangle inequality on the second term. And now I have two terms, which is f plus g p minus 1 times f plus f plus g p minus 1 g. So I need to estimate one of them, and the other one is similar. So now recall that f plus g p minus 1 times f. Well, I'm going to choose I'm going to again use the Holder's inequality, but here I see I need two conjugate values like this equals to 1. But I'm going to choose S to be P over P minus 1. But in this case, you know that if S equals to P over P minus 1, that just means that S is a conjugate of P. And here S is also a conjugate of R, so that just means that R equals to P. Okay, so you just see R equals to P. So now I'm just going to use two. One is this as my new P, and the P itself as my new Q. Okay, so I'm going to use that here. So this is less than, by Holder's inequality, this is less than equal to F plus G P minus 1 with the power P minus 1, and the times the F of P. Okay, so this is like the Q, this is like the P now. Okay, and what this one is, we can just compute it, P minus 1, and then I have the power P over P minus 1. So this times P minus 1, and then outside I have this P minus 1 over P. Okay, and I have this FP here. Now I can see that this will cancel, and I have just the P's power left for this, and then I have another 1 over P outside as the power here, and I have a P minus 1 as extra, so it's just a F plus G, it's the P's power to the power, P norm of that to the power P minus 1 times the FP. Okay, and similarly we have, we can show the second term. So this now is less than equal to that. Okay, and the second term is similar, so it's just less than equal to F plus G P minus 1 times F P plus the same thing P minus 1 and the G P norm of G. And now you can see that the left hand side here is equal to the F plus G P norm to the power P, and the right hand side both terms have this and this, so we can divide both sides by this term. Then the left hand side is just F plus G P. The right hand side will only have this FP plus GP left. Okay, so that's the Minkowski inequality.